In this video, we're going to go over the KutaSoftware Infinite Calculus free worksheet, evaluating limits, and this is evaluating limits at removable discontinuities. Before we jump into this worksheet, I want to go over a few ways to support my channel and me. First of all, by liking and sharing these videos or subscribing to my channel is one of the most important ways that you can show your support. Secondly, become a patron. And to find out more about becoming a patron, go to my website, maymap.com, or go to my Patreon page, which I'll leave a link in the description below. Now, back to the worksheet. So if we're evaluating limits at removable discontinuities, that's points where the function seems to have a hole, or it has a completely different value than what it would appear to have. So let's look at number 1. In number 1, we're looking at the limit of f of x as x approaches 2. So you can see that f of x is negative x squared plus 2 for all values that are not 2. But when x equals 2, we're at negative 5 for f of x, which is this point here. However, unlike direct evaluation, where we were able to plug in a and solve, if we were to plug in a, we would have x equals 2, which would give us negative 5. But that's not the limit. The limit we have to evaluate, remember, from the right and the left, which occurs for this piece of the function. So as we're coming from the left, we're approaching negative 2, and as we're coming from the right, we're approaching negative 2 for f of x as we approach 2 for x. Therefore, that is the limit. The limit is negative 2 for number 1. So again, the limit does not necessarily equal what that function is at that point. Looking at number 2, you can see that there is a hole when x is equal to negative 2. And that's because negative 2 plus 2 equals 0, and dividing by 0 is undefined. But we can still calculate that limit. As we approach negative 2 from the left, we're getting closer to f of x equaling 4. And as we approach negative 2 from the right, again, we're getting closer to f of x equal to 4. Therefore, our limit in number 2 is 4. So as x approaches negative 2, the function of x approaches 4. In numbers 3 and 4, we're to evaluate each limit. You may use the provided graph to sketch the function. And you can see at that point, if we were to plug in 3 for x, we would have 3 minus 3, which equals 0. Therefore, we're going to have a discontinuity when x is equal to 3. But let's graph and see what that limit would be. And I'll graph using an online graphing calculator, but feel free to use a t-table if you want. So typing in my function, I have x squared minus 7x plus 12, and that's all over x minus 3. So you can see that I have a straight line with intercepts at 0, negative 4, and 4, 0. So I'll go ahead and plot those 2 points to draw my line. However, remember we know that we have a discontinuity at x equals 3. So if we were to find x equals 3, you can see that we are indeed undefined. And that's at approximately negative 1 for f of x. So that is going to be a hole, or in other words, a removable discontinuity. So here's our function with our hole at 3, we're undefined. And you can see from this graph, as we approach 3, we're getting closer and closer to negative 1. And as we approach 3 from the right, looking at those values, we're getting closer and closer to negative 1 as well. But at that point, it's undefined. So because our function f of x approaches negative 1 as x approaches 3, that is our limit. Now I want to show you one more way that we can calculate this limit, and that's by replacing the limit with an equivalent limit that can be evaluated. And there's 2 separate ways you can do that. One, you can factor and cancel out, in other words, factoring and simplifying, or the second way is to use the conjugates. So in number 3, we can factor and simplify. So factoring the numerator, we need to see what two numbers multiply to give us 12 and add to give us -7. And that's going to be -4 and -3. -4 times -3 is a +12, and -4 plus -3 is a -7. So the factored form of our numerator is x minus 4 times x minus 3. And that's all over our denominator of x minus 3. But look, x minus 3 can cancel out with x minus 3 to leave us with x minus 4. So the limit as x approaches 3 of our function is equivalent to the limit as x approaches 3 of an equivalent function, x minus 4. However, just to note, these are equivalent for all values where x is not equal to 3. But now, because we factored and canceled, we no longer will get a 0 in our denominator when we plug in 3. So plugging 3 in for x now, that gives us 3 minus 4, which equals a -1, which is what we got when we graphed. Let's move on to number 4. In number 4, let's start off by factoring in order to solve for our limit. So the numerator will stay as x plus 3, but the denominator, what multiplies to give us -3 and adds to give us a +2. That's going to be -1 and +3. So we'll have x minus 1 times x plus 3 and the denominator. And you can see that x plus 3 in the numerator cancels out with x plus 3 in the denominator to leave us with 1 over x minus 1. Now we'll take that value and plug it in, because now when we plug -3 in, we do not get 0 in the denominator, so we can solve. So that will be 1 over -3 minus 1, which equals 1 over -4, or -1/4. So that's the solution of our limit of f of x as x approaches -3. In other words, as x approaches -3, f of x approaches -1. But quickly, let's graph that. And here we have our function, and you can see that we do indeed have a removable discontinuity. When x equals -3, that function is undefined, although it approaches -1/4 from both the left and the right. We do indeed have a hole. Also note we have a vertical asymptote at x equals +1. So let's go ahead and sketch this. Feel free to pick out points and plug them in for x and y, making sure to draw that hole for when x is equal to -3. So when x is -3, our hole is at f of x -1/4. To the left of that, we're slowly approaching 0. And then if we were to plug 0 in for x, we'd be at -1 in the y, or -1 for f of x. So connecting that with a slight curve. And then remember, we have a vertical asymptote at x equals 1. And then for the other side of our function at 2, we're at +1. So that's 1 point. And remember that vertical asymptote, so we're coming from +infinity when we draw our curve and then heading towards 0. And that's how you graph number 4. The important part is to have that vertical asymptote at x equals 1 and to make sure we have that hole at -3, because that shows that at -3 in the x we're at a removable discontinuity or a hole. And that limit, again, was -1/4. Now let's move on to the next section. In our next section, we're evaluating each limit. We're evaluating the limit of f of x as x approaches 0. When x is equal to 0, f of x, or f of 0, is 2. However, when x is not 0, we're using this part of the function. So as we're approaching from the left and as we're approaching from the right, we're using x plus 1. So that's what we're going to use when solving for our limit. And in order to do that, we're going to plug in 0 for x to get 0 plus 1 equal to 1. So our limit as x approaches 0 is 1. Now on to number 6, we have the same kind of ordeal. We have the limit of f of x as x approaches 3. At x equal to 3, we're given that the function is equal to 2. However, for x values to the left and to the right of 3, we're using this equation, 2 plus x over 2. And that's what we're going to use when solving for that limit. So we're taking 2 and then adding that to x over 2, where x we're plugging in a value of 3. So that's 3 over 2, which from here, I'll write this over a common denominator. And 2 in terms of halves is 4 halves. So 4 halves plus 3 halves equals 7 halves. So 7 halves is our limit in number 6. Now, for number 7, we cannot plug 1 in, because if we were to plug 1 in, we would get 0 for the denominator. So we're going to factor. And the part we can factor is the numerator, x squared minus 1. So I'll rewrite this as the limit as x approaches 1 of negative, factoring our numerator, x squared minus 1. We're going to see what multiplies to give us negative 1 and adds to give us 0. Well, that's 1 and negative 1. So in our numerator, our factored form is x minus 1 times x plus 1. And that's all over x minus 1. Now you can see that x minus 1 cancels out with x minus 1. So an equivalent limit is the limit of the opposite of x plus 1 as x approaches 1. And that's equivalent for all values with the exclusion of x equal to 1. So now, because of that, we'll be able to plug 1 in for x. So plugging 1 in for x, we'll get negative 1 plus 1, which equals a negative 2. So negative 2 is our limit in number 7. And quickly, I just want to show you that those functions are indeed equivalent with the exclusion of the point x equal to 1 by graphing quickly. So our old function is the opposite of x squared minus 1 over x minus 1. And you can see, looking at that, we have a straight line with a removable discontinuity at x equal to 1. At x equals 1, that function is undefined. But if we type in the opposite of x plus 1, you can see that it falls on that same line. The lines are essentially interchangeable, except now when looking at the orange line at x equals 1, we're at negative 2 in the y. So those functions are equivalent for all values with the exclusion of 1. So for all values where x does not equal 1. So now that we've went over that, let's continue on to number 8. In number 8, we're going to be factoring again, and I'm going to be factoring that numerator. So this is going to be equal to the limit as x approaches 5 of factoring that numerator. I'm going to pull out an x from each of my terms. So I'll have x times taking an x from x squared, that will leave me with x, and then I'm subtracting, taking an x from 5x, that'll leave me with 5. So x times x minus 5 is my numerator, and in my denominator, I still have x minus 5. And you can see that x minus 5 will cancel out, because x minus 5 divided by x minus 5 is 1, and 1 times any number is that original number. So now we have the limit of negative x as x approaches 5. So we can use direct evaluation at this point and plug in 5 for x. Doing so will give me negative 5 for my limit. So negative 5 is our solution in number 8. And number 9, factoring again. So I have the limit of my function as x approaches 2. However, I'm going to factor that function. So we have negative, or the opposite of, let's factor this numerator. What multiplies to give us negative 2 and adds to give us a negative 1. That's going to be negative 2 and positive 1. So the factored form of x squared minus x minus 2 is x minus 2 times x plus 1. And that's all over x minus 2. So you can see that my x minus 2 will cancel out with x minus 2 to leave me with the limit of the opposite of x plus 1 as x approaches 2. Now what I'll do, I'll plug 2 in for x to solve. So that'll be negative 2 plus 1, which equals negative 3. So negative 3 is the solution for number 9. Now on to number 10, I'm going to factor again, and I'm factoring the numerator again. So we have the limit of our function as x approaches negative 5. And we have to factor because if we plug negative 5 into the denominator, negative 5 plus 5 will give us 0, and it is possible to factor. So factoring the numerator, x squared plus 3x minus 10, we're going to see what two numbers multiply to give us negative 10 and add to give us a positive 3. And that's going to be positive 5 and negative 2. So x plus 5 times x minus 2. And then we have x plus 5 still in our denominator. X plus 5 cancels out with x plus 5, so these limits are equivalent. The limit of x squared plus 3x minus 10 over x plus 5 is equal to the limit of x minus 2 as x approaches negative 5 for all values excluding when x is equal to negative 5. So what I'll do now, I'll be able to plug negative 5 in for x. So I'll have negative 5 minus 2 equal to negative 7. So negative 7 is my solution in number 10. The limit of f of x as x approaches a, or x approaches negative 5, is equal to f of a, which is negative 7. But if we were to try to plug negative 5 in for x, at the start, we would get 0 in our denominator, which we know is undefined. Now on to number 11. I'm going to find a common denominator in my numerator in order to simplify. So what I'll do, I'll multiply the first term by 4 over 4 and the second term by negative 4 plus x over negative 4 plus x. So 4 over 4 times 1 over negative 4 plus x plus negative 4 plus x over negative 4 plus x times 1 over 4. And that's all over x. So you can see when I multiply out that numerator, I'll have 4 over 4 times negative 4 plus x plus negative 4 plus x, because negative 4 plus x times 1 is negative 4 plus x, and that's all over 4 times negative 4 plus x. And remember, this is all divided by x. Now I can simplify because I can add my numerators together. So 4 minus 4 is 0, so I'm left with x in my numerator. So I'll have x all over 4 times negative 4 plus x. But as opposed to writing this all over x, remember dividing by a number is the same as multiplying by that reciprocal. So I'm just going to write this as multiplying by 1 over x. And you can see that when I do this, my x's will cancel out. The x in my numerator will cancel out with the x in my denominator to give me 1 over 4 times negative 4 plus x. So the limit of this function as x approaches 0 is equivalent to the limit of 1 over 4 times negative 4 plus x as x approaches 0, with the exclusion of when x equals 0. But now, when I plug 0 in to the denominator, I can actually solve. So that's going to give me 1 over 4 times negative 4, because when I enter in 0, negative 4 plus 0 is negative 4, and 1 over 4 times negative 4 is 1 over negative 16, or negative 1/16. That is my solution for number 11. Now on to number 12. Again, we're going to start by finding the common denominator, but this time we're finding the common denominator among the denominators. So I'll have x all over 1 over 3 plus x will get multiplied by 3 over 3. So 3 over 3 times 1 over 3 plus x minus 1/3 will get multiplied by 3 plus x over 3 plus x. So 3 plus x over 3 plus x times 1/3. And I want to reiterate that when I'm multiplying by 3 over 3, I'm multiplying by 1, so I'm not changing the value of that first term. And when I'm multiplying by 3 plus x over 3 plus x, I'm again multiplying by 1 and not changing the value of that second term. So now let's multiply that out. I'll have x all over 3 times 1 is 3, and 3 times 3 plus x I'll write as 3 times 3 plus x. And then my next term, 3 plus x times 1 is 3 plus x, and 3 times 3 plus x we know is 3 times 3 plus x. So now that I have a common denominator, I'll be able to simplify. 3 minus 3 is 0. So I'll have x all over negative x, because I'm subtracting that x, over 3 times 3 plus x. And just like in the previous problem, I'm going to now multiply by that reciprocal. So I'll have x times negative 3 times 3 plus x all over x. And again, my x's will cancel out. Therefore, the limit of our function as x approaches negative 3 is equivalent to the limit of negative 3 times 3 plus x as x approaches negative 3. So plugging in negative 3 for x, I'll have negative 3 times 3 plus negative 3, which is negative 3 times 0, which equals 0. So 0 is my solution in number 12. Now moving on to number 13, we can see some radicals. So right away we know we're going to simplify using conjugates. So I'm going to be multiplying x minus 5 over the square root of x plus 4 minus 3 by that conjugate of the denominator. So it's going to be the square root of x plus 4 plus 3 over the square root of x plus 4 plus 3. And if you have trouble understanding conjugates, please refer back to a tutorial lesson or to a conjugates worksheet and do some practice problems before continuing on. Now when I'm multiplying by this conjugate, I need to FOIL. First, outside, inside, last, and you can see that because I have negative 3 times the radical and I have 3 times the radical, when I add those together, that will be 0. So I really only need to concentrate, because this is a conjugate, my first terms and my last terms. So I'll have x minus 5 times the square root of x plus 4 plus 3, and that's all over the square root of x plus 4 times the square root of x plus 4 is x plus 4, because the square root squared cancels out that square root, and then I have negative 3 times 3, which is a negative 9, so minus 9. Now from here, I'll leave my top as two binomials, because when I simplify my denominator, x plus 4 minus 9 is x minus 5. And now, x minus 5 cancels out with x minus 5. So the limit of my function as x approaches 5 is equivalent to the limit of my new function, the square root of x plus 4 plus 3, as x approaches 5. So all I'm going to do is direct evaluation. Take 5, plug that in for x, and solve. So the square root of 5 plus 4 plus 3 is the square root of 9 plus 3, which equals 3 plus 3 and gives me a value of 6. So 6 is my solution in number 13. Now in number 14, again, I'm going to be multiplying by the conjugate, but this time it's going to be the conjugate of that numerator. So multiplying by the conjugate over the conjugate is going to be the same as multiplying by 1, so I'm not changing this value. So I'm going to do the square root of x plus 6 plus 3 over the square root of x plus 6 plus 3. And again, I only need to look at, because this is the conjugate, my first terms and my last terms, multiplying them out, because the inside and outside will add together to give me 0. So the square root of x plus 6 times the square root of x plus 6 is the square root of x plus 6 squared, which is just x plus 6. And then negative 3 times a positive 3 is a negative 9, so we'll be subtracting 9. And then our denominator will have x minus 3 times the square root of x plus 6 plus 3. Now that's going to equal x minus 3 in the numerator, and then in my denominator I still have x minus 3 times the square root of x plus 6, then plus 3. So you can see that x minus 3 cancels out with x minus 3 to give me that the limit as x approaches 3 of 1 over the square root of x plus 6 plus 3. So the limit of this new function as x approaches 3 is equivalent to the limit of my original function as x approaches 3. So plugging in 3 for x, I'll get 1 over the square root of 3 plus 6 plus 3, which is 1 over the square root of 9 plus 3, which is 1 over 3 plus 3, which gives me 1/6. So 1/6 is my solution for the limit in number 14. Now on to our critical thinking questions. It says to give an example of a limit of a rational function where the limit at negative 1 exists, but the rational function is undefined at negative 1. So essentially, we want something where the denominator equals 0 when x is negative 1. So when x equals negative 1, x plus what value equals 0? And that's going to be a positive 1. So my denominator is going to be x plus 1. So I'll have the limit of my function as x approaches negative 1. And my denominator, I'll have x plus 1. And for my numerator, I'll make that x squared minus 1. Which, if I was to factor x squared minus 1 out, I would get x plus 1 times x minus 1. So that would be all over my denominator of x plus 1. And when I cancel out x plus 1 and x plus 1, my limit as x approaches negative 1 of my function is equivalent to the limit as x approaches negative 1 of x minus 1. So technically the rational function is undefined because plugging in negative 1 gives me 0, but the limit does exist. There's an equivalent limit that we can calculate. So again, we wanted something with x plus 1 in the numerator so that x plus 1 would cancel out with x plus 1. We could have made that something else. We could have made that, let's say, x plus 3. When we factored that out, that would give us x squared plus 4x plus 3 over x plus 1, but we can still factor and cancel out that x plus 1, but the limits would still be equivalent with our new example. So go ahead and try and figure out an example of your own and put it in the comments below. And lastly, number 16, it says give two values of a where the limit cannot be solved using direct evaluation, and then give one value of a where the limit can be solved using direct evaluation. So right away we know that one denominator cannot equal 0 because that's undefined. So negative 2 plus x equals 0. That x value will give us an undefined answer, as well as if this denominator equals 0. 1 over negative 2 plus x plus 1 over 2 equals 0. Solving for either of those will give us an undefined answer in our function. So let's solve. I'll add 2 to both sides in this first equation to get x equals a positive 2. We know that the limit when x equals 2 cannot be solved, so a cannot be equal to 2. It also cannot be equal to another number. So for this, I'm going to subtract 1/2 from both sides to get 1 over -2 plus x equal to -1/2. Now we can continue solving, or I can recognize that 1 over -2 plus 0 would be -1/2. And -1/2 would indeed equal -1/2. So a can also not be 0. And again, what I did is if I plugged 0 in for x, I got -1/2, and -1/2 plus a +1/2 is 0. And that was easier to see once I moved my fraction to my other side. But if you did not pick up on that, feel free to continue to solve for x, and you will indeed get 0. So a cannot be 2, and it cannot be 0, but a can be any other number. It says to give one value of a where the limit can be solved, but in all honesty, a can equal any other number. So we can pick a number such as 5. We can pick a number such as -30, and so on. So a cannot equal 2 and 0, but a can equal any other number. And with that, we wrap up the evaluating limits at removable discontinuities worksheet. If you have any questions, as always, leave them in the comments below, as well as your examples from number 15. And as I went over in the first part of this video, you can support me by liking, subscribing, sharing, and by becoming a patron. Click the link below to find out more on that.